Lawrencium. Lawrencium is a synthetic chemical element with symbol Lr and atomic number 103. It is named in honor of Ernest Lawrence, inventor of the cyclotron, a device that was used to discover many artificial radioactive elements. A radioactive metal, Lawrencium is the 11th transuranic element and is also the final member of the actinide series. Like all elements with atomic number over 100, Lawrencium can only be produced in particle accelerators by bombarding lighter elements with charged particles. 12 isotopes of Lawrencium are currently known. The most stable is 266Lr with a half-life of 11 hours, but the shorter-lived 260Lr is most commonly used in chemistry because it can be produced on a larger scale. Chemistry experiments have confirmed that Lawrencium behaves as a heavier homologue to lutetium in the periodic table, and is a trivalent element. It thus could also be classified as the first of the 7th period transition metals. However, its electron configuration is anomalous for its position in the periodic table, having an s2p configuration instead of the s2d configuration of its homologue lutetium. This means that Lawrencium may be more volatile than expected for its position in the periodic table and have a volatility comparable to that of lead. In the 1950s, 1960s, and 1970s, many claims of the synthesis of Lawrencium of varying quality were made from laboratories in the Soviet Union and the United States. The priority of the discovery and therefore the naming of the element was disputed between Soviet and American scientists, and while the International Union of Pure and Applied Chemistry initially established Lawrencium as the official name for the element and gave the American team credit for the discovery, this was re-evaluated in 1997, giving both teams shared credit for the discovery but not changing the element's name. In 1958, scientists at the Lawrence Berkeley National Laboratory claimed the discovery of element 102, now called nobelium. At the same time, they also attempted to synthesize element 103 by bombarding the same curium target used with nitrogen-14 ions. A follow-up on this experiment was not performed, as the target was destroyed. 18 tracks were noted, with decay energy around 7000900000000000000 black spade 9 plus or minus 1 MeV and half-life around 14s. The Berkeley team noted that while the cause could be the production of an isotope of element 103, other possibilities could not be ruled out. While the data agrees reasonably with that later discovered for 257Lr, the evidence obtained in this experiment fell far short of the strength required to conclusively demonstrate the synthesis of element 103. Later, in 1960, the Lawrence Berkeley Laboratory attempted to synthesize the element by bombarding 252Cf with 10B and 11B. The results of this experiment were not conclusive. The first important work on element 103 was carried out at Berkeley by the nuclear physics team of Albert Ghiorso, Torbjörn Sikoland, Almon Larsch, Robert M. Latimer, and their co-workers on February 14, 1961. The first atoms of Lawrencium were reportedly produced by bombarding a 3 mg target consisting of 3 isotopes of the element californium with boron-10 and boron-11 nuclei from the heavy ion linear accelerator. The Berkeley team reported that the isotope 257,103 was detected in this manner, and that it decayed by emitting an 8.6 MeV alpha particle with a half-life of 700080000000000000000 black spade 8 plus or minus 2s. This identification was later corrected to be 258,103, as later work proved that 257Lr did not have the properties detected, but 258Lr did. This was considered at the time to be convincing proof of the synthesis of element 103, while the mass assignment was less certain and proved to be mistaken. It did not affect the arguments in favor of element 103 having been synthesized. Scientists at the Joint Institute for Nuclear Research in Dubna raised several criticisms, all but one were answered adequately. The exception was that 252Cf was the most common isotope in the target, and in the reactions with 10B, 258Lr could only have been produced by emitting 4 neutrons, and emitting 3 neutrons was expected to be much less likely than emitting 4 or 5. This would lead to a narrow yield curve, not the broad one reported by the Berkeley team. A possible explanation was that there was a low number of events attributed to element 103. This was an important intermediate step to the unquestioned discovery of element 103, although the evidence was not completely convincing. The Berkeley team proposed the name Lawrencium with symbol LW, after Ernest Orlando Lawrence, inventor of the cyclotron. The IUPAC Commission on Nomenclature of Inorganic Chemistry accepted the name, but changed the symbol to LR. This acceptance of the discovery was later characterized as being hasty by the Dubna team. The first work at Dubna on element 103 came in 1965, when they reported to have created 256,103 in 1965 by bombarding 243 am with 180, identifying it indirectly from its granddaughter fermium-252. The half-life they reported was somewhat too high, possibly due to background events. Later 1967 work on the same reaction identified two decay energies in the ranges 8.35 8.50 MeV and 8.50 8.60 MeV. These were assigned to 256,103 and 257,103. Despite repeated attempts, they were unable to confirm assignment of an alpha emitter with a half-life of 8 seconds to 257,103. The Russians proposed the name Rutherfordium for the new element in 1967, this name was later used for element 104. Further experiments in 1969 at Dubna and in 1970 at Berkeley demonstrated an actinide chemistry for the new element, so that by 1970 it was known that element 103 is the last actinide. In 1970, the Dubna group reported the synthesis of 255,103 with half-life 20 s and alpha decay energy 8.38 MeV. However, it was not until 1971, when the nuclear physics team at the University of California at Berkeley successfully performed a whole series of experiments aimed at measuring the nuclear decay properties of the Lawrencium isotopes with mass numbers from 255 through 260, that all previous results from Berkeley and Dubna were confirmed, apart from the Berkeley's group initial erroneous assignment of their first produced isotope to 257,103 instead of the probably correct 258,103. All final doubts were finally dispelled in 1976 and 1977 when the energies of X-rays emitted from 258,103 were measured. In 1971, the IUPAC granted the discovery of Lawrencium to the Lawrence Berkeley Laboratory, even though they did not have ideal data for the element's existence. However, in 1992, the IUPAC Transfermium Working Group officially recognized the nuclear physics teams at Dubna and Berkeley as the co-discoverers of Lawrencium, concluding that while the 1961 Berkeley experiments were an important step to Lawrencium's discovery, they were not yet completely convincing, and while the 1965, 1968, and 1970 Dubna experiments came very close to the needed level of confidence taken together, only the 1971 Berkeley experiments, which clarified and confirmed previous observations, finally resulted in complete confidence in the discovery of element 103. Because the name Lawrencium had been in use for a long time by this point, it was retained by IUPAC, and in August 1997, the International Union of Pure and Applied Chemistry ratified the name Lawrencium and the symbol LR during a meeting in Geneva. Lawrencium is the final member of the actinide series and is sometimes considered to be a group 3 element, along with scandium, yttrium, and lutetium, as its filled F shell is expected to make it resemble the 7th period transition metals. In the periodic table, it is located to the right of the actinide nobelium, to the left of the 6d transition metal rutherfordium, and under the lanthanide lutetium with which it shares many physical and chemical properties. Lawrencium is expected to be a solid under normal conditions and assume a hexagonal close-packed crystal structure, similar to its lighter congener lutetium, though this is not yet known experimentally. The enthalpy of sublimation of Lawrencium is estimated to be 352 kJ/mol. Close to the value of lutetium and strongly suggesting that metallic Lawrencium is trivalent with the 7s and 6d electrons delocalized, a prediction also supported by a systematic extrapolation of the values of heat of vaporization, bulk modulus, and atomic volume of neighboring elements to Lawrencium. Specifically, Lawrencium is expected to be a trivalent, silvery metal, easily oxidized by air, steam, and acids, and having an atomic volume similar to that of lutetium and a trivalent metallic radius of 171 pm. It is expected to be a rather heavy metal with a density of around 15.6 to 16.6 G/cm3. It is also predicted to have a melting point of around 1900 K, not far from the value for lutetium. In 1949, Glenn T. Seaborg, who devised the actinide concept that elements 89 to 103 formed an actinide series homologous to the lanthanide series from elements 57 to 71, predicted that element 103 should be its final member and that the Lr3+ ion should be about as stable as Lu3+ in aqueous solution. It was not until decades later that element 103 was finally conclusively synthesized, and this prediction was experimentally confirmed. 1969 studies on the element showed that Lawrencium reacted with chlorine to form a product that was most likely the trichloride LrCl3. Its volatility was found to be similar to that of the chlorides of curium, fermium, and nobelium, and much less than that of rutherfordium chloride. In 1970, chemical studies were performed on 1,500 atoms of the isotope 256Lr, comparing it with divalent, trivalent, and tetravalent elements. It was found that Lawrencium co-extracted with the trivalent ions, but the short half-life of the 256Lr isotope precluded a confirmation that it eluted ahead of Md3+ in the elution sequence. Lawrencium occurs as the trivalent Lr3+ ion in aqueous solution, and hence its compounds should be similar to those of the other trivalent actinides. For example, Lawrencium fluoride and hydroxide 3 should both be insoluble in water. Due to the actinide contraction, the ionic radius of Lr3+ should be smaller than that of Md3+, and it should elute ahead of Md3+ when ammonium alpha hydroxyisobutyrate is used as an eluent. Later 1987 experiments on the longer-lived isotope 260Lr confirmed Lawrencium's trivalency and that it eluted in roughly the same place as erbium, and found that Lawrencium's ionic radius was 7001886000000000000 black spade 88.6 plus or minus 0.3 pm, larger than would be expected from simple extrapolation from periodic trends. Later 1988 experiments with more Lawrencium atoms refined this value to 6989881000000000000 black spade 88.1 plus or minus 0.1 pm and calculated an enthalpy of hydration value of 2993631500000000000 black spade 3685 plus or minus 13 kJ/mol. It was also pointed out that the actinide contraction at the end of the actinide series was larger than the analogous lanthanide contraction, with the exception of the last actinide, Lawrencium. The cause was speculated to be relativistic effects. It has been speculated that the 7's electrons are relativistically stabilized, so that in reducing conditions, only the 7p1/2 or 6d electron would be ionized, leading to the monovalent Lr end ion. However, all experiments to reduce Lr3+ to Lr2+ or Lr end in aqueous solution were unsuccessful, similarly to lutetium. On the basis of this, the standard electrode potential of the E-degree couple was calculated to be less than 1.56 V, indicating that the existence of Lr end ions in aqueous solution was unlikely. The upper limit for the E-degree couple was predicted to be 0.44 V. The values for E-degree and E-degree are predicted to be 2.06 V and plus 7.9 V. The stability of the group oxidation state in the 6D transition series decreases as RFIV dBV SGVI, and Lawrencium continues the trend with LRIII being more stable than RFIV. In the molecule Lawrencium dihydride, which is predicted to be bent, the 6D orbital of Lawrencium is not expected to play a role in the bonding, unlike that of lanthanum dihydride. LaH2 has Law H bond distances of 2.158 A, while LRH2 should have shorter LRH bond distances of 2.042 A due to the relativistic contraction and stabilization of the 7s and 7p orbitals involved in the bonding, in contrast to the core-like 5f subshell and the mostly uninvolved 6d subshell. In general, molecular LRH2 and LRH are expected to resemble the corresponding thallium species more than the corresponding lanthanide species. The electron configurations of LR and LR2+ are expected to be 7s2 and 7s1 respectively, unlike the lanthanides which tend to be 5d1 as Ln2+. However, in species where all three valence electrons of Lawrencium are ionized to give at least formally the Lr3+ cation, Lawrencium is expected to behave like a typical actinide and the heavier congener of lutetium, especially because the first three ionization potentials of Lawrencium are predicted to be similar to those of lutetium. Hence, unlike thallium but like lutetium, Lawrencium would prefer to form LRH3 than LRH, and LRCO is expected to be similar to the also unknown LUCO, both metals having a valence configuration of sigma-2pi1 in their respective monocarbonyls. The p-pi-d-pi bond is expected to be observed in LRCl3 just as it is for LuCl3 and more generally all the LnCl3, and the complex anion is expected to be stable just like its lanthanide congeners, with a configuration of 6d1 for Lawrencium. This 6d orbital would be its highest occupied molecular orbital. A Lawrencium atom has 103 electrons, of which 3 can act as valence electrons. In 1970, it was predicted that the ground state electron configuration of Lawrencium was 5f146d17s2, following the Aufbau principle and conforming to the 4f145d16s2 configuration of Lawrencium's lighter homologue lutetium. However, the next year, calculations were published that questioned this prediction, instead expecting an anomalous 5f147s27p1 configuration. Though early calculations gave conflicting results, more recent studies and calculations confirm the S2p suggestion. 1974 relativistic calculations concluded that the energy difference between the two configurations was small and that it was uncertain which was the ground state. Later 1995 calculations concluded that the S2p configuration should be energetically favored, because the spherical s and p1/2 orbitals are nearest to the atomic nucleus and thus move quickly enough that their relativistic mass increases significantly. In 1988, a team of scientists led by Eichler calculated that Lawrencium's enthalpy of adsorption on metal sources would differ enough depending on its electron configuration that it would be feasible to carry out experiments to exploit this fact to measure Lawrencium's electron configuration. The S2p configuration was expected to be more volatile than the S2d configuration, and be more similar to that of the p-block element lead. No evidence for Lawrencium being volatile was obtained, and the lower limit for the enthalpy of adsorption of Lawrencium on quartz or platinum was significantly higher than the estimated value for the S2p configuration. In 2015, the first ionization energy of Lawrencium was measured, using the isotope 256Lr. The measured value, 4.96 plus 0.080.07 eV, agreed very well with the relativistic theoretical prediction of 4.963 eV, and also provided a first step into measuring the first ionization energies of the trans-actinides. This value is the lowest among all the lanthanides and actinides, and supports the S2p configuration as the 7p1/2 electron is expected to be only weakly bound. This suggests that lutetium and Lawrencium behave similarly to the d-block elements, and also that Lawrencium may behave similarly to the alkali metals sodium and potassium in some ways. Given that the S2p configuration is correct, then Lawrencium cannot be regarded as a transition metal under the IUPAC definition, unlike its lighter homologue lutetium and the group 3 elements, with which lutetium and Lawrencium are sometimes classified. It is nevertheless quite likely that metallic Lawrencium will behave similarly to curium, which has an 5f76d17s2 configuration, and show the expected 5f146d17s2 configuration, which is supported by the earlier volatility experiments. 12 isotopes of Lawrencium are known, with mass numbers 252, 262 and 266, All are radioactive. Additionally, one nuclear isomer is known, with mass number 253. The longest-lived Lawrencium isotope, 266Lr, has a half-life of 10 hours and is one of the longest-lived superheavy isotopes known to date, suggesting that it is perhaps on the shore of the island of stability of superheavy nuclei. However, shorter-lived isotopes are usually used in chemical experiments because 266Lr currently can only be produced as a final decay product of even heavier and harder to synthesize elements. It was discovered in 2014 in the decay chain of 294Ts. The isotope 256Lr was used in the first chemical studies on Lawrencium. Currently, the slightly longer-lived isotope 260Lr is usually used for this purpose. After 266Lr, the longest-lived Lawrencium isotopes are 262Lr, 261Lr, 260Lr, 256Lr, and 255Lr. All other known Lawrencium isotopes have half-lives under 20 seconds, and the shortest-lived of them has a half-life of only 390 milliseconds. However, the undiscovered isotopes with mass numbers 263 to 265 are expected to have longer half-lives. The half-lives of Lawrencium isotopes mostly increase smoothly from 252Lr to 266Lr, with a dip from 257Lr to 259Lr. While the lightest and heaviest Lawrencium isotopes are produced only as alpha decay products of dubnium isotopes, the middle isotopes can all be produced by bombarding actinide targets with light ions. The two most important isotopes, 256Lr and 260Lr, are both in this range. 256Lr can be produced by bombarding californium-249 with 70 MeV boron-11 ions, while 260Lr can be produced by bombarding berkelium-249 with oxygen-18. Both 256Lr and 260Lr have half-lives too short to allow a complete chemical purification process. Early experiments with 256Lr therefore used rapid solvent extraction, with the chelating agent thenoyl trifluorostone dissolved in methyl isobutyl ketone as the organic phase, and with the aqueous phase being buffered acetate solutions. Ions of different charge will then extract into the organic phase under different pH ranges, but this method will not separate the trivalent actinides, and thus 256Lr must be identified by its emitted 8.24 MeV alpha particles. More recent methods have allowed rapid selective elution with alpha HIB to take place in enough time to separate out the longer-lived isotope 260Lr, which can be removed from the catcher foil with 0.05 m hydrochloric acid.